today we're going to look at magnetic fields. Look at it beyond just magnets, what causes them. So, what creates a magnetic field other than a magnet? Moving charged particles. This is going to be foundational fact number one. What causes a magnetic field? What creates magnetic field? Moving charged particles. So if you had current flowing through a wire, would that create a magnetic field? Absolutely. You got moving charged particles going through that wire. So what would it look like? So let's say we have current. This is a wire here. What would that look like if you had current flowing through it? You have moving charged particles. It's not something you would expect. They're concentric rings with the wire at the center. What does that mean? Here are two examples of that. You got a wire with current shown by the red arrows, and then the magnetic field is with capital B, and that's showing. So we have concentric rings where the wire's at the center. So the variable that describes magnetic field is a capital B. The equation for the strength of the magnetic field near a wire, a long straight wire, is equal to this constant times current over 2 pi times R. You're not going to need to calculate this per se. You just need to know how it works. Like I'll give you this equation, but you need to know as different variables increase and decrease, what happens to the strength of the magnetic field. So based off of this, what would cause magnetic field to increase? Well, you could either increase the current flowing through the wire, increase I, or you could decrease R. They're inversely related with R, so that means you get closer to the wire. So this is a crazy thing called a right-hand rule. This is something in physics that if you talk to people who've taken physics, you're like, oh yeah, the right-hand rule. So what you do is pretend your pencil is the wire, and you stick your thumb in the direction of current, and your fingers wrap around in the direction of the magnetic field. Okay, something like that. Okay, so so fingers represent the direction of the magnetic field. Your thumb represents the direction of the current through the wire. So in order to handle this, we need to deal with three-dimensional vectors. So we've got right, left, up, down. That's easy. But what about like into the page and out of the page? Okay, so out of the page represents a circle with a dot. That's like an arrow coming at it. So it's a little different for you and me, but let's pretend you're looking at it. You're looking at the arrowhead, circle the dot, okay, as it comes out of the page at you. Circle with the X represents like an arrow with the feathers as you look away as it comes out of, like it goes into the page, so it's going into the page away from you. That was from your point of view, not my point of view. I was trying to bring that out. So the camera angle, that's away from the page, going, sorry, into the page. Man, that might have been really confusing. We'll talk about it in class. All right. So, all right. So if you had current going through going through a loop of wire, what would the magnetic field look like? It would look something a little like that. Let's readjust where we camped out here. All right, so you still have this curl going around this wire, but it's twisted, and the overall effect is you get magnetic field going all in the same direction in the middle, which is a huge thing. So we're adding up all that. The strength of the magnetic field at the center here is going to be represented by this equation here, magnetic field in a loop. You get this constant times current over 2 times the radius being the radius of the loop itself. So this would be R, capital R, versus in the previous thing, lowercase r would be how far you are away from, that would be lowercase r. Okay, so increase the current or decrease the radius, increase the magnetic field. Then you have another thing. Let's say we have a bunch of loops together. It's called a solenoid. If we wrap it together or tight and pass current through that in this direction, what happens? What does that create? It creates a magnetic field that looks a little something like this. Craziness. This is a little more basic drawing, but this is the top one here is more three-dimensional. So there's an equation for this one as well. That one is the magnetic field of a solenoid is equal to the constant over the number of loops over the length times the current. So L represents this length. Capital N would represent 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think I counted 16 at one point. Anyway, so that would be 16 loops over whatever that length is. A lot of times we just write that as this ratio of number of loops per meter, loops per length, unit length, is often how we do that. So how could we increase the solenoid strength of the magnetic field by the solenoid? You could increase the current. You could also increase the number of loops per meter, more densely packed or on top of themselves. And finally, this sets us up for an electromagnet. We're creating a magnet without necessarily a magnet because we're creating a magnetic field. So how do we capitalize on that? The magnetic field, electromagnet, you just take some kind of piece of iron, something ferromagnetic, helps strengthens it. You wrap the wire around it in loops, and then you pass current through it, and ta-da, you've got an electromagnet, something you can turn on and off. And there you go.